In our previous lesson, we took a look at the vector equation of a plane, and I have the review of that right here, or the summary of that here. We're going to continue looking at the idea of a plane, just a different representation this time, which is a Cartesian equation of a plane. In a previous lesson, we looked at the Cartesian equation of a line in R2, and I mentioned there that we would still be using the Cartesian equation in R3, but it would no longer be the equation of a line. It would actually end up being the equation of a plane. So we're going to take a quick look at where that comes from, and then from there we're going to make use of it. So the vector equation of a plane starts off with an initial position vector. So that essentially defines a single point in the plane. And obviously you have infinite points to choose from there, but you just arbitrarily choose one, or one is given to you. And then it is made up of two direction vectors. These direction vectors have to be non-collinear, otherwise they don't form a spanning set, and we need to span a plane. And then we have our scaling coefficients, and so S is a member of R and T is a member of R. They can take on all values, all real values, including 0. If S and T are equal to 0, that just happens to describe the point of the initial position vector. So that means that if we start off with some starting point, x0, y0, and z0, and we describe the vector to any other point in the plane is going to be to the point x, y, and z. In other words, the vector r, which is from the origin to x, y, and z, then that means that a vector that must lie within this plane can also be defined generically as from this starting point to any point, any other point on the plane. So to say that another way, on this plane we have our starting point P0 that is given to us by the initial position vector. There must be some other point, and as a matter of fact there are infinite numbers of other points on this plane. So I'm going to arbitrarily choose one of the points that lies on this plane as x, y, z. That means that the vector from P0 to P has to be defined by x minus x0, y minus y0, z minus z0. Now that's the long way around to get to this, but you'll see where I'm going, hopefully, in a moment. So if this is a vector in the plane, then, so we have to imagine that we have a plane, and I'm just going to very crudely represent that. So there is a plane, so it's this area that I put these squiggled lines on the sides just to indicate that it extends indefinitely in all directions. If we have the point P0 and that forms a vector to the point P, sorry, I shouldn't have put a vector symbol above that. This, however, is the vector P0, P. Then I can draw a normal to this plane. Not only is this going to be normal to the plane, but if it's normal to the plane, it must be normal to the vector P0, P. So I'm going to call that my vector n. And I'm going to give that vector components a, b, and c. Then if these are perpendicular, if this normal vector is perpendicular to the plane, which means it's specifically perpendicular to P0, P, then the dot product must be equal to 0. I can evaluate that dot product algebraically. And so this definition gives me that I don't need to write the letter n again. I'm actually going to write it out as a, b, c dotted with x minus x0, y minus y0, z minus z0 is equal to 0. And now I go ahead and I apply my rules for dot product. So that means a gets multiplied by x minus x0 plus b multiplied by y minus y0 plus c multiplied by z minus z0. and that's equal to 0. And then that becomes ax minus ax naught plus by minus by naught plus cz minus cz naught is equal to 0. Now, the points or the values x naught, y naught, and z naught are the only ones here that have a single definition. They came from our initial position vector. So what I'm going to do is, first of all, I'm just going to write ax plus by plus cz minus ax naught minus by naught minus cz naught is equal to 0. And just for the sake of convenience, I'm going to take those last three terms because they're made up of a, b, and c. Those are going to be what we've defined as the normal vector of the line, and a, b, and c are still represented here. X naught, y naught, and z naught are the initial position vector for the plane. Sorry, I said line a moment ago, for the plane. And so I end up with the equation ax plus by plus cz plus d is equal to 0. And this is the Cartesian equation of a plane. Now, you might think that I've pulled a fast one here with what I've done about setting this to d, but you have to remember our starting point could have been an actual position vector and an actual pair of direction vectors. And when we talk about the idea of normal to the plane, we actually do have the math required for that. For example, we could say that the normal vector was equal to direction vector 1 crossed with direction vector 2, for example, and that would be valid. So I could come up with this equation using the values that I was given to define the plane as a vector equation. Now here's a representation you're going to see quite a bit when it comes to trying to describe a plane. When you're trying to describe a plane with a two-dimensional surface, such as our viewing surface here in this video, it's difficult. Of course, the surface of the screen is a two-dimensional surface, but then it gets difficult to show the idea of a normal vector. So quite often you end up drawing this, you have to imagine this as a rectangle that's kind of laid down flat, and you've got these two dotted lines represent, for example, direction vectors within that plane. And then we have the normal vector, which quite clearly comes out of that plane. And in this case, because it's normal, it comes out at a 90-degree angle. Whenever we write the Cartesian, which is sometimes called the scalar equation of a plane, you have to write it in this form. Ax plus by plus cz, those make up your normal vector components. And then the constant d defines the other properties of the plane. And as we saw before, that d actually represents information about your initial position vector for the initial point that you're starting with on the plane. I've talked about the Cartesian equation before. The coefficients a, b, and c are generally member of the integers. So that's a convention we try to follow when we're going to write something in the Cartesian form. So find the Cartesian equation of the plane that contains the point 251 and is perpendicular to the line given by this vector equation. Now, I'm not going to always recommend you do a sketch here because, as I've mentioned, this is something that's quite difficult for people a lot of the time to sketch these things. I'm going to put together a sketch just to give you a better idea as I explain through this. So, and I'm not going to worry about where these things actually appear in my coordinate systems. I guess I should pay a little bit of attention to this one. My initial position vector has an x of 0, But then the y is 3, the z is 1. So the point is I have my initial position vector there. And then I have a direction vector, and I'm not even going to worry too much about this direction vector. But this direction vector, let's say, looks like that. So there is my direction vector. And that means that my line that we're talking about here looks something like this. Now we want actually a plane that is perpendicular to that line. So, and this is where it gets difficult to imagine things. So now we've got a plane, and I'm just going to kind of draw it so that that line goes through the middle of the plane or through the body of the plane. So let's say it kind of punctures the plane right there. Well, that means that the direction vector that we originally drew, that direction vector actually has to be perpendicular to the plane, because the idea is the direction vector punches straight through that plane, and that means it's perpendicular. But that means that this is my normal vector. My normal vector is actually already given to me by that direction vector. And so as a result, that gives me my values a, b, and c for my Cartesian equation, which has the form ax plus by plus cz plus d equals 0. And so now I can write that as 2x plus 4y plus z plus d equals 0. And then the only thing I need to do now is make use of this point, which also lies on the plane. So I'm going to sub in the point 2, 5, 1, and let's make sure I'm making it clear that that's a point, not a vector. And so I get 2 times 2 plus 4 times 5 plus 1 plus d equals 0. I have 4 and 20 and 1, that's 25. Bring it to the other side, that's negative 25. And so the equation of my plane is 2x plus 4y plus z minus 25 is equal to 0. That's the Cartesian equation of this plane that I have drawn very badly and has very little to do with the reality of the situation. I was just trying to illustrate this. Find a Cartesian equation of any generic plane perpendicular to the xy plane. Now to do this, I think what I'm going to do is I'm going to try to illustrate 2 or 3 possibilities here. Perpendicular to the xy plane. So first of all, here's the xy plane, and if it helps you, imagine this as the floor of the room, whatever room you happen to be in. So a perpendicular plane, if you were holding a flat piece of cardboard, what would it mean for that to be perpendicular to this floor? Well, it would mean it was standing up vertically on the floor. So you might imagine something like that, where this is the edge that's in contact with the floor. You might imagine something over here, where this is the edge in contact with the floor. You might imagine something over here, where this is the edge in contact with the floor. And I don't know how good a job I've done of drawing these. With this one in particular, what I was trying to show you was the x-axis is coming out and actually being perpendicular. And so that would mean the I vector is perpendicular there. Over here, the j vector would be perpendicular. And then at this point, we would have some combination of the I vector and the j vector. And we could actually, if we were holding this piece of cardboard, we could continue to slide it in a circle. We could actually go anywhere around. We could move further away from the origin, closer to the origin. What is the only thing that all of these vectors have in common with each other? And the thing they have in common is that their z component is 0. So that means that my normal vector can actually be any value of A, any value of B, but my C value has to be 0. So that's the first thing. So we end up with our equation is AX plus BY plus 0 for C plus D is equal to 0. But other than that, we could also have any point. And so that means that D stays generic. So D is also generic. So this is actually the equation, the Cartesian equation of any plane, or this is actually the equation of every plane if you want to think of it, every plane that's perpendicular to the xy plane. Example 3, find the scalar equation of the plane defined by this set of parametric equations. Now, it might be more convenient here if I were to write these in a slightly more organized way, which is going to be the constant, and then I'm going to put the p value and then the q value. The constant first, the p value second, and the q value third. And the constant first, which in this case is 0, plus the p value minus the q value. Now the reason I'm doing that is just so I can actually, it might be easier to put this into a vector form first. And that's why I did this, because now I can see that my initial position vector is 2, 3, 0. If I put the value s there, actually I don't need to put the value s, I can put the value p. I already have my scale factor. And that's going to be positive 1, negative 1, positive 1. And then q is going to be negative 1, positive 4, negative 1. And so now that I have my two direction vectors, from here, my normal, I just need anything that's going to be perpendicular to this plane in order to describe it using a normal. And so I can just take 1, negative 1, 1, crossed with negative 1, 4, negative 1. And when I go ahead and do that, I am going to write it out over here, I guess. So I, j, k, I, and then 1, negative 1, 1, and 1, negative 1, 4, negative 1, and negative 1. And so my x component is going to come from here, from these two. That's going to give me my x component. And so I'm going to get negative 1 times negative 1 is positive 1 minus 1 times 4. So that's 1 minus 4. And then I'm going to get my y component is going to come from these two. And so that's going to be 1 times negative 1 is negative 1 minus 1 times negative 1, but that's minus a negative, so that's going to be plus 1. And then I get my z component from here. 1 times 4 is 4 minus negative 1 times negative 1 is positive 1, so that's going to be minus 1. And I end up with negative 3, 0, 3. And so there's my normal vector. From there, it's a fairly short step to now write negative 3x plus 0y plus 3z plus d is equal to 0. And in order to find my value for d, I'm going to need to sub in a point. But do I know a point? Yes, I do. I know that is my initial, well, that's my vector to my initial point, but I can sub in that point. So I end up with negative 3 times 2 plus 0 times y, so that's just going to be 0, plus 0 times z, let's put that one in, plus d is equal to 0. So I end up with, that's equal to -6, so d is equal to +6. So here at this step, I subbed p0. And so now I can write my equation -3x plus 3z plus 6 is equal to 0. But I'm not actually done in this case, because I can actually divide everything, not by 2, I can divide everything by 3. 3 is a common factor, so there's no point in keeping that. So I end up with -x plus y plus 2 equals 0. And I've mentioned to you before that there's a bit of a convention where normally we try to have this first term be positive. So I could also write that as x minus y, pardon me, that's supposed to be plus z, which becomes x minus z minus 2 equals 0. And that's probably the kind of solution you're going to see, for example, in a solution set or in your textbook. State the coordinates of 3 points on the plane. Now you might wonder, this is one of those ones where it's easy to overcomplicate things. In this case, all we really need to do is sub in some values. So for example, what is the easiest value to put in here for x? That would be a 0. What is the easiest value to put in here for y? That would be a 0. And then from there, we have to get our value for z. So when I sub in a 0 here and a 0 here, I end up with z equals -4. So it's just like when you're subbing in to find the, if you have a straight line, y equals mx plus b, and you're asked to graph it by plotting points. You put in x's and you solve for the y's. Well, now we have to sub in 2 different values. So from here, I could go, for example, 1, 0, and that's going to give me, if I put a 1 in here, that's 2, 0 there makes that easy, and then I end up with 2 plus 4 is 6, so z equals -6. And then how about I go, actually it looks like, how about I go 2, 0, because I don't want to deal with the 5 times y. You can make a strategic choice like that. So 2 times 2 is 4, 4 plus 4 is 8, so I end up with z equals -8. So these are 3 points on the plane. Now the thing you have to be careful of is you can't, when we make the vectors for these things, we have to watch out that they are not collinear. And if I take a look at this, I actually have produced that. I've produced something collinear. So that's not going to work out. I need to vary things a little bit. And so how about I put in x equals 1 and y equals 1. And so then I get 2 minus 5 is -3, plus 4 is 1, so that goes to -1. And then instead of x equal 2, well, I could have stayed with x equal 2 there. And how about y equals 1? So then I get 4 minus 5 is -1, plus 4 is 3, gives me -3. And so this is point 1, this is point 2, this is point 3, which means I can now, I've stated 3 coordinates, so we've got point 1, 0, 0, -4, point 2, 1, 1, -1, point 3, 2, 1, -3. And I realize this first part only wanted 3 points. I was actually thinking ahead to the second part already. So what I did the first time through was perfectly fine for answering this first part. How do we change the Cartesian equation of a plane into a vector equation? So if I start with this Cartesian equation, I can find 3 points, and if I can find 3 points such that the vectors are non-collinear, for example, the vector p1 and p2 or p1, p3, if I can arrange it so that those vectors are non-collinear, then I know that my vector equation, I can actually make these into my direction vectors. And I already know my original position vectors because this is the same as OP1. This is the same as OP2. This is the same as OP3. And so I know I have 3 choices for my initial position vector. I have 3, and actually 6 if you include the opposite vectors. For my direction vectors, I have to choose 2 of those 6 so that they're non-collinear. And then I could turn my Cartesian equation into a vector equation. The important part here is that D1 and D2 must be non-collinear. So you might have to check that. Just check and see whether or not one of these is a scalar multiple of the other. If we are comparing individual planes, the scalar equation or the Cartesian equation is useful because it deals with normals, and that's actually how we compare planes to each other. So the idea of 2 planes being parallel just means that their normal vectors are scalar multiples of each other. 2 planes being perpendicular comes down to this very simple expression. Their dot product of their normals is 0. And then we get into this kind of strange thing, which is going to probably require a physical demonstration in class, when we talk about the angle between 2 planes. So if 2 planes intersect each other, we can actually come up with the angle of intersection between 2 planes. And it's just given by the dot product of those 2 planes divided by the magnitudes of the normals, the dot products of the normals over the magnitudes of the normals. And that's exactly how we have found the angle of intersection between 2 lines. Same mathematical procedure. Okay, that's it for this one. Hopefully it wasn't too long, but again, my feeling of it is I went a little long. Apologies for that.